Okay, so welcome back, and let's get started about 3.2 derivative as a function. Okay, so last class in 3.1, this is what we learned. Give you a function f of x, and we defined the derivative of the function at a specific point, right? Let's see, x0, which is defined into a limit format. H limit as h approaches 0, f of x0 plus h minus f of x0 over h, right? And you see that this, again, is the derivative at that specific point, okay? But now, if I replace my x0 into the variable x, and f prime of x is the limit as h approaches 0, f of x plus h minus f of x over h. This is the derivative of the function f of x with respect to the variable x. Okay, with respect to the variable x. So let me stand in this sign. And as you can see, guys, after you evaluate this limit here, and then the format, most of the time, it can be a function involved with variable x. There are some situations the derivative it could be a constant. That's okay, but but even a constant, it's still we can treat it as a constant function. So meaning here, guys, the derivative of fx with respect to the variable x itself, this expression itself is also a function. Okay, it's a function. So that's the main thing about the derivative as a function. And if f prime of x exists at a particular x, then we have a name. We call that f of x. It is differentiable at that specific x. Okay. And think about it this: if f prime of x it exists at every point in its own domain, then we also have a name for this function, which that function is called differentiable. Okay, so differentiable. Differentiable at a point. If the derivative exists for each of the points in its interval, then the function is called differentiable. Okay, so just some concept. Now let's move on. Again, we talked about the notation in section 3.1, and we're going to carry over with the notation here. F prime of x, which stands for the derivative of fx with respect to x. We can also rewrite this into df dx or d dx, then f of x here, okay? Well, basically, it's the derivative of fx with respect to x. Again, those two notations, these are called the Leibniz notation. Leibniz is, a great mathematician, and is also the created calculus. Okay, so he and Newton, they both created calculus. So often, during the history, a lot of argument about who's the number one to create the calculus. Okay, you know, yeah, so that's a little bit background. So now let's talk about one example, and then we're going to talk a little bit more about the derivative as a function. Okay, so look at this example, very simple here. Fx equals x squared, which we know that it's a problem, graph is here, and figure out what is f prime of x. Okay, so let's do that. F prime of x, as the previous slides just mentioned, is defined as limit as x approaches 0, f of x plus h minus f of x over h. Okay, over h. So this is definition. F of x plus h based on fx equals x squared, which is x plus h squared, which gives us is x squared plus 2xh plus h squared. Okay. F of x, meanwhile, equals x squared. So this f prime equals limit h approaches 0. And I just replace here, guys. Okay, so x squared plus 2xh plus h squared minus, right? This is f of x plus h minus x squared over h. And clearly you can see that x squared minus x squared cross out. And there is a 2xh plus h squared on the top over h. So you can easily to simplify this, because the top you can factor h and make the cancellation. So let me write into this with h times 2x plus h over h, right? So h and h is cross out. Hence this limit gonna become limit as h approaches 0 to x plus h, and we know that limit equals 2x. Okay, you know that. So that's actually, it's the derivative of the function f of x, f prime of x. So you see f prime of x, we just calculated here, equals 2x. And we all know that 2x, which is a line, right? Which is a line. So let's see how do we interpret that, guys. You see, let's see if I have different things. Okay. So, you know, if I start with some places here, I'm starting to draw the slope of the tangent line, and I do agree that that slope actually, it's gonna be a very small slope, right? Like negative 100 or something. And then as your x is becoming larger and larger and larger, and then do you see that the slope of the tangent line, it actually is increasing, right? Although it's negative. And then at this moment, when x equals 0, do you see that it's gonna become 0 because the slope of the tangent line is horizontal, and then no, the tangent line is horizontal, and then the slope of that tangent line equals 0, right? So do you see that this is exactly described like from a very negative number, increasing, when x equals 0, dot, slope of the tangent line equals 0. Well, let's see what happens after we cross the 0 here. And then do you realize that after here, the slope, it becomes a positive, right? Right? And then that slope of the tangent line is becoming larger, 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 and larger, and larger. And do you see that after the slope of the tangent line becomes 0, it becomes larger, 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 larger,